And we start. So let's recall what we did last time. Last time we started studying nonlinear models. We are given a sample point, and then we are given a fitting function which fits those points. And this function is dependent on the parameters a1 up to ap. And the model is nonlinear in the sense that the dependence of this function on these parameters is not linear, but it could be nonlinear. So we allow functions of those parameters to appear in the definition of capital F. And since we want that this function fits our data, we get a bunch of equations. They're written here. So F evaluated in the point xi and with these parameters should be equal to yi. Here we had few examples. We won't go over them again. And then we started studying how to solve such a system. So we have a system of equations which are nonlinear in unknown parameters, and we would like to find approximate solutions. We said that it's impossible, usually it's impossible to find analytic solution. So formulas with which we express A1 up to AP. So we need approximate solutions. So we need some numerical methods to find those solutions. And for those numerical methods to work, it's much more appropriate to transform the system, our initial system, into such a system. So we put all the numbers into on one side of the equations, and we have zeros on the other side. So in fact, we are searching for the zeros of few functions which depend on few parameters. So in this case, functions are g1 up to gm, and parameters are a1 up to ap. So we are talking about vector functions in this case. So we have capital G. It depends on, so it maps from p tuples into m tuples. So since it maps from p tuples, it's called the function of a vector variable. And since it maps into m tuples, it's called a vector function. And we're searching for its zeros. If m is equal to 1, so if here, if we are mapping into r to the power of m, then we have a usual multivariate function. And if also p is equal to 1, then we have a usual univariate function, so function of one variable. A special case of a vector function of a vector variable is a linear vector function. So a linear vector function, for a linear vector function, we can express, the rule of this function in this form. So g of x is just a times x, where a is a matrix and x is a vector of variables. And we were dealing with such functions when we were solving linear models. But why are we talking about linear vector functions again? This is because the algorithms which solve nonlinear models in fact use linear vector approximations at each step. So last time we were studying Newton's method. In Newton's method, it goes for a iterative method where on each step we approximate our function in the neighborhood of the approximate with a linear function of this type, and then do one step of the method with a linear function, and then calculate in the new point, calculate a new linear approximation, and proceed in this way until we converge to some solution. Okay, and if we allow also a non-zero constant part, so if we allow here plus some vector b, then we are talking about affine linear functions. So if you recall a tangent method from analysis, how we are trying to solve some function, some equation of a function of one variable. We are searching for its zero. What we can do is we choose a point like here, and then we calculate the tangent, and where the tangent meets the x-axis is a new approximate. And then in this new approximate, we again go up to the graph of the function, calculate a new approximate, and calculate a new tangent, and then again compute where this tangent meets the x-axis, which is then a new approximate. So this is how we would solve one equation of one variable. But if we want to generalize this method to more variables and more equations, then we need to first generalize the notion of a derivative of a function. And for this aim, we introduced so-called Jacobian matrix. So we have a function f. This is a function which has more coordinate functions. It has m coordinate functions, and each of those coordinate function is dependent on n variables. And taking the derivative of this vector function capital F is calculating the Jacobian matrix. So in the first row of the Jacobian matrix, we take all the partial derivatives of the first coordinate function, f1, with respect to all variables, so x1 up to xn. And then in the second row, we take the partial derivatives of the second coordinate function with respect to all the variables, and so on. For example, if you have m is equal to 1, so if you have a function and it has more variables, then this Jacobian matrix will have only one row. And if you recall from analysis, what does this row represent? This row represents a gradient of the function. So this is nothing else but the gradient. Jacobian matrix of a multivariate function of a multivariate function which maps into r to the power of 1 is just the gradient. And this picture represents the geometric meaning of the gradient. We are in the point x0, y0. We calculate the function value in this point, f of x0, y0, and we get k. This is some number. And then we calculate also all other points x, y, such that the function value on those points is k. And what we get is this level curve, this green level curve. This is just the definition of a level curve. And then we calculate the gradient of the function in this point x0 and y0, and we get this violet vector. And as you recall from analysis, this gradient is then perpendicular to this level curve, which means that it's perpendicular to the tangent on this curve. So this is always the case, that gradient is perpendicular to the level curve in the point. For general M and M, Jacobian matrix is just a vector which has for rows gradients of the coordinate functions. And then what we did last time is we took also a linear vector function. So this is a affine linear vector function. F of x is ax plus b, and calculated the Jacobian matrix of this function. And we noticed that Jacobian matrix of this function is just the matrix A. So it's just the coefficient at the vector of variables x. And the idea of a linear approximation of a vector function f is to do an approximation of this function in the given point by a affine linear function. And the two conditions we would like that this affine linear function meets are given here. So we would like that this function has the same value as the initial function f in the point where we approximate it. So linear approximation in the given point is equal to the function of the given point. And we also like that the derivative, so the Jacobian matrix of the linear approximation, coincides with the Jacobian matrix of f in this point. And it's a matter of easy calculation that the appropriate linear approximation is exactly as given here. So LA of x is f of a, this is some vector, plus a Jacobian matrix of f in a, calculated in a, times the difference between x and a. So this nicely generalizes the situation where when n is equal to m is equal to 1. And again, if you recall from analysis, the linear approximation of a function of two variables, so the function maps into R, the linear approximation is just the tangent plane in the point where we calculate the approximation. So we have here our function f. This is its graph. This blue one is the graph of our function. It's some surface. And then we approximate it linearly, as we explained on the last page, in the point P. And it turns out that what we get is just the tangent plane to this surface in this point. So we could draw a nice picture only when n is equal to 2 and m is equal to 1. If n was 3, then we would need 4 dimensions to draw such a picture. So this doesn't go through. So only n is 2 and m is 1 could be visualized. And here is one example. So we have a function of 3 variables mapping into r to the power of 2. And here is the calculation of the linear approximation. Okay, and then we studied Newton's or tangent method to solve solve an equation f of x is equal to 0. So as I said before, we have this graph of the function. We are in the point. This is our initial point x0. We calculate the tangent. The tangent meets the x-axis in x1. We go up to the graph, calculate a new tangent, calculate the intersection with the x-axis, and proceed in this way. And if we choose x0 good enough, then this will converge to the solution. So to the solution of this initial equation, f of x is equal to 0. It's usually hard to choose a good initial approximation. So we had this theorem, last time we looked at this theorem, which ensures that in an interval from where we can choose the initial approximation always exists, is if the function has a simple 0 on this, has only simple, if the derivative has only simple zeros. I mean, if the function has only simple zeros on the interval I, which means that the derivative doesn't have zeros on the interval I. So if the function has only simple zeros on some interval, then we're always able to choose an interval from where every initial approximation will be good. This is the content of this theorem. However, this theorem says nothing about how to choose this interval I. And this is usually a very hard task to choose interval I in advance. So we have to, the easiest way is to try different x naught, and see if it converges, if the procedure converges. Okay, and then we generalize this method to higher n and m, but n was the same as m. So function mapped from n tuples into n tuples. And the generalization was that in every point we calculate this linear approximation and calculate the intersection of this, calculate the zero of this linear approximation, one of the zeros of this linear approximation. So we solve this equation. We see that the next iterate is just the previous iterate minus inverse of the Jacobian in the previous iterate times the function value in the previous iterate. And we said that it's usually numerically not stable to calculate the inverse of the Jacobian. It's better to solve a linear system. So we transformed this equation into this equation. So we multiply it with Jacobian and get Jacobian times the movement which we have to make is minus the function value in the point. And this is just the usual linear system, which we solve, for example, by a LU decomposition. If you use the backslash operator in MATLAB, it uses the LU decomposition with partial pivoting to solve this system. And then the new approximate is just the previous one plus the solution of this equation. Okay. And let's look at this example. We have two equations, and both are of both consist of two variables, and we would like to find a common solution. So it's we can write this as a vector function mapping from r to the power of 2 into r to the power of 2. We said that we want to transform the system so that on the right side we get only zeros. That's why we put -1 on the left and then -25 on the left again and get this vector function f. And then use Newton's method to find zeros of this capital F. So we calculate the Jacobian of f. In the first row, we have partial derivatives with respect to the first function. So the first one is 2x minus 10. And then the second one is 2y plus 1. In fact, this 2y plus 1 should be written here. And then the partial derivatives of the second coordinate function. And we get 2x minus 1. So this is that one, which, so I swapped, when I typed this into a TeX form, I swapped 2x minus 1 and 2y plus 1. So it should be interchanged. And then the derivative with respect to y of this function is minus 2y plus 10. And now we can use Newton's method to calculate approximate of the zero. And let's do this in Octave, or better in MATLAB. So this is these are our coordinate functions. Before I try to find the solution, I will draw those graphs to see where how many intersections I can expect and where approximately those intersections will be. So this is for drawing implicit functions. There is a rule F implicit in MATLAB, and I would like only to remark that this F implicit doesn't work in Octave. So if you will try to use this in Octave, it's not implemented yet. So we run this example. And what we get is this blue curve and this red one. And let's look. So the first one is if we transform the first one, then we get just the equation of a circle. So x minus 5 squared plus y minus plus 1/2 squared plus something. So this is just the equation of the circle. So this f, the graph of f, is this blue one. And if you look at the second one, then we would get x minus 1/2 squared, and then minus, and y plus 5 squared. So it would be hyperbola. And this is this red one. And you can see that we can expect two intersections. So if we run our Newton's method, then for some initial approximates, we will converge to this intersection. And for some other initial approximate, we will converge to this other intersection. And we can see that this the first intersection has coordinates approximately 2, 4. So let's try to use Newton's method with the initial approximate x is 2 and y is 4. So this is my function as an inline function, and this is Jacobian matrix. And we will use Newton's method for initial approximate 2, 4. And see, you see what we get. So already after 5 steps, we converge, because the relative error, I mean, the relative difference between the last two approximates is 10 to the power of minus 17. So we stop the iteration, and the intersection is then 1.96 and 3.62. So this is somewhere here. So this is here. So 1.96 and 3.62. And then to determine the other intersection, we'll do the same, only that now we will change the initial approximate. So we will take, for example, 10 minus 2 would be good. Let's see what I took. 8 minus 3. Okay, let's take 8 minus 3 for the initial approximation. And again, we converge already after 6 steps, and the solution is x is 9.09 and y is minus 3.57. So it's always good to know an approximate picture of our functions, so that we know how many intersections how many intersections or how many solutions we expect, and where approximately we expect the solutions. Otherwise, we could, if we didn't have this picture, then we wouldn't know how many solutions this system have, and where those solutions lie, and if really calculate all the solutions. So it's always good to know approximate picture of our situation. Okay, and this is where we stopped last time. And now we will generalize this to systems which won't be square systems. So this system was square system, meaning that the number of constraints was the same as the number of unknowns. But now we would also like to solve systems where we will have more constraints than unknowns, or vice versa. But usually there will be more constraints than unknowns.
Just a quick question. The diagonal elements 2x minus 1 and 2y plus 1 are switched, yes?
Yes,
Okay,
they are switched, yeah. Here they are switched, but in the MATLAB script they were okay. Otherwise, the solution wouldn't be. The method would converge somewhere which wouldn't be even a solution. Okay, so before we look at this Gauss-Newton method for rectangular systems, let's say another application of this Newton's method. This application is in Newton's optimization. So application of Newton's method. In optimization. So by now we had function f, which was a vector function mapping from r to the power of n into r to the power of n, and we were searching for its zeros. So f of x equals to 0, and this x, we were searching for x. But now in the optimization, this method could be used in this way. So we have a function, a multivariate function from r to the power of n, and since it's a usual function, it maps into r. So it's usual function. Now we don't want to calculate its zeros, but we would like to calculate its extrema. We are searching for local extrema of this function. So not zeros. If we would like to find zeros, then we could use tangent method. But we are not searching for the zeros, but for local extrema. Now, you remember from analysis, the candidates for extrema are stationary points. So critical or stationary points. The candidates for extrema are exactly stationary points. This means that a point is stationary if all the derivatives, all the partial derivatives are equal to 0. So in a compact way, I can write this as gradient of f. So this is now a function, a vector function of a vector variable, mapping from from r to the power of n into r to the power of n. So this gradient in the local extremum must be 0. So I will write the local extremum with a, and it should be 0. So local extrema, and I will write here A. So if A is a local extremum of F, then it should be a 0 of the gradient. And what we achieved now, so we start with a usual multivariate function, and we would like to find its extrema. And now we transform this problem into searching zeros of the gradient. So those problems are not equivalent, but we know that if A is extremum of F, then it should be a 0 of the gradient. So not every 0 of gradient is extremum of F, but if A is an extremum of F, then it should be 0 of the gradient. And now we have this vector function gradient F of a vector variable, and we can use Newton's method to calculate its zeros, to approximate its zeros. So by Newton's method, we can approximate zeros of this gradient F. And I will write it as capital F. And we know that for Newton's method, we need to calculate the Jacobian of F. So we need Jacobian of F, of capital F. And I will write it down. So Jacobian of F in the point X. This is just, so this is a matrix. So let's write, so this capital F, this is a vector function with coordinate functions, derivative of F with respect to x1, then derivative of F with respect to x2, and so on. And now in the first row of the Jacobian, I take partial derivatives of this first coordinate function. So I take derivative of F, of partial derivative of F with respect to x1. Again, I take the derivative with respect to x1. Then I take the derivative with respect to x2, and so on. So in fact, writing this in a compact way, I can write, so this is a function f, and then I derive it, I differentiate it twice with respect to x1. And then I have a function f, and I differentiate it first with respect to x1, and then with respect to x2, and so on. So those are second derivatives of the function f with respect to different variables. And I do the same for the other functions, for the other coordinate functions. So f of x2 derive with respect to, differentiate with respect to x1, then f of x2 differentiate with respect to x2, and so on. And in the second row, so I get the, again, second derivatives of f with respect to, so if I'm in the ith row and jth column, then I take the derivatives with respect to xi and xy, xj. and so on. So do you remember from analysis how we call this matrix? When we were studying the local extrema of a function of two variables, then so we calculate stationary points. This means that we calculate zeros of the gradient, and then we have to determine if the zeros are local minima, local maxima, or if they are not extrema. And we had to calculate this matrix of second derivatives, and we call this Hessian, so Hessian of f. And we will denote it by h of f. So this will be h of f calculated in the point A. So this means that we plug in here A, and the same in the second row. So how does Newton's method for capital F then look like? So Newton's method for capital F, recall that this is just the gradient of small f. This is, so we choose x naught, and then we do the iteration. Xk plus 1 is xk minus, and then Jacobian of capital F, but we just saw that Jacobian of capital F is just the Hessian of small f. So Hessian of small f calculated in xk, and then we take inverse times, and then here we have value of f in the point xk, so capital F. So you have to be careful not to swap things here. So we have Hessian of small f, which is just the Jacobian of capital F, and since we are doing Newton's method for capital F, here we are calculating the function value of capital F in the point xk.
So what is the difference between Hessian of small f and Jacobian?
Jacobian of small f is the matrix of first derivatives. I mean, it's like that, yeah. For small f, Jacobian, what's the Jacobian? The Jacobian of small f has only one row because we have just one component function, and Jacobian of small f is then gradient. So yeah, we can write this is a little bit confusing here. We have small f, this is a usual function, and then we can compute Jacobian of f, of small f, is gradient, so it's a function from r to the power of n into r to the power of n. So it's just gradient of f. But the Hessian of f, so it's again r to the power of n, so it's a matrix. It's again r to the power of n into r to the power of n. But this is the matrix of second derivative, so we have f of x1, x1, f of x1, x2, and so on, f of x1, xn, then f of x n x1 and so on. It's usually symmetric. But gradient, this is just so it is a function where you have f of x1 up to f of x n. So yeah, here yeah, what's the difference? So here it's n. Of course, it's n squared. Since so we have a Hessian, it maps from n tuple, it maps it into a matrix. It maps it into n times n matrix. So we can write it here as n times n. But gradient of f maps n tuple into a vector, into an n times 1 vector. So a Hessian is one dimension, has one, it's appropriate, it's a bigger matrix. Gradient is only a vector, but the Hessian is a matrix.
So in gradient, there's a first derivative, and in Hessian, there are second derivatives.
Yeah, and we have n squared second derivatives, but in the Jacobian, we have only n possible derivatives.
Yes, thank you.
So this is one way for applying Newton's method in Newton's optimization, but you have to be careful not to swap things. So we have to have Hessian of small f and capital F here. Okay, and now we generalized all this to Gauss-Newton method. So in Gauss-Newton method, our function maps, our vector function maps from n tuples into m tuples, and n and m can be different from each other. And of course, we cannot expect that the system f of x is equal to 0 is solvable. If let's assume here that n is bigger than m, this will be a usual situation when there will be no, vice versa, when there will be more constraints than variables. So we have n variables and m constraints, and m is bigger than n. So this n is number of variables. And this m is number of constraints. So usually such a system will have more constraints than variables, and we cannot expect that it will be solvable. There will be rarely common solution of all the constraints. But we already know that then we are searching for the solution by the least square method. So, but we are searching for the solution of the system by the method of least squares. Which means that we are searching for alpha such that the norm of f of alpha will be minimal among all norms f of x when x runs over all possible vectors. So That means that in the solution alpha, the following will be true. Norm of f of alpha is smaller or equal to the norm of f of x, where x runs over all possible tuples. So it's smaller or equal to norm of f of x for all x. Okay, and maybe it's time for a break, and we proceed in 15 minutes.
One quick question before the break.
Yes.
I must have forgot the exact thing from analysis, but the gradient is zero in a static function because all the partial derivatives in each direction are zero, right?
Yes.
Okay, thank you.
Yeah, this is just the compact way of saying that all the partial derivatives are zero. So we just collect them in a vector, call this vector gradient, and then we say that gradient must be zero. So we ended the first hour by this condition. We are solving a rectangular system. F of x is equal to 0. There are n variables in x, and there are m constraints, and we assume that m is bigger than n. Of course, we cannot expect exact solution of this system. The exact solution doesn't even exist usually, but we are searching for the solution by the method of least squares. So this means that we are searching for alpha, such that the norm of alpha, f of alpha, so this is some vector if in r to the power of m. So the norm of this vector will be the smallest possible. So the smallest possible meaning that we go over all n tuples, calculate the norms of vectors f of x, and so f of alpha, norm of f of alpha is smaller or equal to f of x. So in other words, this is equivalent to writing that norm of f of alpha is minimal of the norms among the norms f of x, where x runs over n tuples. So Gauss-Newton method for searching alpha is the following. In the first step, it's an iterative method, so we choose initial approximate, x naught, this is n tuple, which is initial approximate. And then we improve this initial approximate in this almost the same way as for Newton's method. So the next approximate is previous approximate minus. Then we have Jacobian matrix of f calculated in the previous approximate. And in Newton's method, we took inverse. But here we cannot take inverse since this is a rectangular matrix. But we can take Moore-Penrose inverse times f on the previous approximate. And why is this good? Let's try to explain why is this second step really good. So the idea behind is the following. So f of x, Taylor approximation, Taylor expansion of this vector valued function f is of the form. So Taylor expansion around point around a of f is the following. So f of x is f of a plus, and then we have Jacobian matrix of f in the point a times x minus a, and then plus, and then we have higher terms, x minus a squared. Of course, we cannot calculate square of a vector, but here we have some error which is dependent on not x minus a squared, because this is a vector and we cannot square it, but on the norm of this vector squared. So this big O notation means that what remains is something, so this is approximately some constant. So the norm of this is approximately what remains is approximately some constant times the norm of x minus a squared. And you see, if x is very near to a, then this error is negligible compared to the linear part. And this linear part is just the linear approximation. F. So this term, negligible compared to linear approximation of f in the point a for x which are near a. And now, so we are searching for the local extremum of f, which means that if we linearly approximate our f, we would like that the norm of this linear approximation is as small as possible. So we are minimizing f of x, norm of f of x. In other words, we are minimizing, this linear approximation of f in the point a. Yeah. So, and now you recall, so what is this? This is just a linear system. We are trying to solve f of a plus Jacobian of f in the point a times x minus a is equal to 0. So our variable is x. We write this in the linear system form. So Jacobian of f in the point a times x minus a is equal to minus f of a. And now you should remember from the linear systems chapter that the solution of this system by the least squares method is nothing else but x minus a is Moore-Penrose inverse of the Jacobian matrix calculated on this left-hand side. So we express x from this. So x is A plus Moore-Penrose inverse of the Jacobian calculated. And I will just change this plus into minus so that I don't need to write minus in the parentheses. So I have here f of A. And this is then our approximate. And if you look above, you see that this is exactly the second step in the Gauss-Newton's method. We have A is equal to xk. And then we do the Taylor expansion of f around xk. Neglect this part of degree 2 or higher. And then we would like to minimize this linear approximation of f in the next point. And then we use what we know from linear systems, that the solution of the system, of the linear system by the least squares method is exactly if we multiply both sides with Moore-Penrose inverse. So this is idea behind Gauss-Newton's method. And I would like only to mention that here for Gauss-Newton method to work, the assumption that we have more constraints than variables is not needed. We could also have the other way around. We could have more variables than constraints and still run Gauss-Newton's method. It's just choosing initial approximate and then calculating the next approximate in this way. But it turns out that in practice, this is not stable. So usually Gauss-Newton method for systems with less constraints than variables just doesn't converge. So using Gauss-Newton's method makes sense for systems with more constraints than unknowns. And there is another remark, which we will also see in the example with MATLAB. So I will write this remark. Gauss-Newton method doesn't give us global extrema, but local ones. So it doesn't necessarily solve our problem. It just gives us local extremum. And then we have to see if this is really what we wanted. So in this, which local extrema we get depends on the initial approximate. So which local extremum we get depends on x naught. So choosing x naught in an appropriate way is also very important. And we will see this shortly in the example. Depends on x naught. So we have to evaluate the solution at the end. The solution at the end. So, for example, what I want to say is we have a function of one variable. Let's say that this is its graph. Let's say that this is the graph or a function. And we are searching for x such that f of x is as small as possible. So what we would like to determine is this x. For this x, f of x, in this case, absolute value is the smallest possible. I will write it x naught is the smallest possible. But the problem of the remark which I wrote, if we choose initial approximate somewhere here, then Gauss-Newton method will converge to this local extremum. So choosing this approximate Gauss-Newton method converges to, I will write here x naught prime to x naught prime, which is far from the solution of our problem. So f of x naught, we're searching for this x naught such that f of x naught is very small, but here this x naught prime is a local extremum, but f of x naught prime is much bigger than it should be. So you have to keep in mind that even if this method converges, it doesn't necessarily give you the right solution. And we will see this on the example. So example. Let's take points in R squared. So in the plane, we have m points, and we would like to feed them with the exponential model. This was the first example when we started to study nonlinear models. So we are searching for the exponential function of the form f of x a b is equal to a times e to the power of bx, which fits our data in the best possible way. So let me draw a picture. So we have here some data, and we are searching for exponential function. It could be either like that, or it could be either like that. So we are searching for this exponential function that fits our data in the best way by means of least squares method. And we can use Gauss-Newton method. So Gauss-Newton method what we want to do, so we want to solve this system f of xi ab is equal to yi, and this is for every point. So for I goes which goes from 1 to m. And as we said at the beginning of this chapter, we put those y's on the left-hand side. So we have f of xi ab minus yi is equal to 0 for every i. So these are our coordinate functions. These are our g of x ab is just f of x ab minus y, and now I plug in the actual the actual rule for f. So this is a times e to the power of bx minus y. So these are our coordinate functions. We have m of them when we plug in every point. So what we will need for the Gauss-Newton method to work is we will need first Jacobian matrix. So our G is now G1, G2 up to Gm. And we need Jacobian matrix of this G, which is so partial derivative of G1 with respect to the first unknown. In our case, the unknown is A. And then partial derivative of G1 with respect to the second unknown, which is B. So what is partial derivative of G1 with respect to A? It is just, so I take the partial derivative with respect to A of this. So I get e to the power of bx1. And then I take the partial derivative with respect to b, and I get a times, and then x1 times e to the power of bx1. And then I repeat for the second coordinate function. So I get e to the power of bx2, and here a times x2 times e to the power of bx2, and so on. So this is our setting. So we have first choose A naught, B naught. This is approximate, initial approximate. And then I improve those approximates. So K plus first approximate will be kth approximate minus, then I have this Jacobian in the point AK, BK times, and then I have my function. And what is my function? My function is G. So I have here G of AK, BK. And of course, I have to take the Moore-Penrose inverse here. Let's do a concrete example. Just let me look in MATLAB which points I've chosen. So I have 202, 107.7, 2. Okay, so I took concrete example. So points were 0, 2, then 1, 0.7, if I remember correctly, and then 2, 0.3, and 3, 0.1, yes. So 1, 0.7, and then 2, 0.3, and 3, 0.1. So those are my points. This is the first one, and then the second one, and then the third one, and then the fourth one. And you see, I would like to find some exponential function that minimizes squares of distances, sum of squares of distances from those points. So those distances I would like to minimize d1 squared plus d2 squared and so on. So what is my G? What is my G? You see here, my G has 4, since I have 4 points, this capital G will have 4 coordinate functions, each for each function for each data point. So G is then G of AB is then has 4 coordinate functions, G1, G2, G3, G4. All those are functions of the unknown parameters A and B. So I have 2 minus e times e to the power of b times x, and my x is 0. So I've plugged in here 2 for y, and then x, 0 for x. And the same for the other 3 points. So we have 0.7 minus a times e to the power of b times 1. So this is this 0.7. This is y, and then 1 for x. And so on. So 0.3 minus a times e to the power of b times 2, and 0.1 minus a times e to the power of b times 3. And my Jacobian in the point AB is then, so I have e to the power of b times 0, this is 1, so it's just minus 1. And 0, since e to the power of b times e to the power of b times 0, this is 1, so this just disappears here from the first equation. This is 1. Then in the other, I take the derivative with respect to a, and I get minus e to the power of b, and then I get minus a times e to the power of b when I take the derivative with respect to b, and the same for the other 2 functions. So minus e to the power of 2b, and then minus a times 2 times e to the power of 2b, and minus e to the power of 3b, and minus a times 3 times e to the power of 3b. So this is my G, and this is my Jacobian. And I can run Gauss-Newton method with some initial approximate AB. If I don't think anything about A and B, I can just say, okay, AB, let's say that the initial approximate is 1, 1. And since I don't want that it's exactly 1, so usually it's good to put here 1 point and something so that you don't have some division by 0. So I will just put 1.1 and 1.1 for the initial approximate, and let's see where we will converge. So this is this function G in my notes. And then this is Jacobian, which we've just computed. And let's run our method with this approximate 1.1, 1.1. So I'm running Gauss-Newton method with this approximation. X is A is 1.1 and B is 1.1. and I run it. Okay. Let me comment this out. I will explain what this surface represents later on. Okay, let's try again. Okay, you see, I run this example. I started with A, B is 1.1, 1.1, and already after 16 steps, the method converged, and A was 0.22, B was 0.38, and the convergence is really, we really obtained convergence because the relative difference between the last two approximates is really small, 10 to the power of minus 17. So this is really a local extremum of our function g. But what does our actual picture looks like? So this is our actual picture. So those are blue points are our data, and this is our exponential function we obtained. You see, it's really bad fit, but it is a local extremum for A and B, which are near 1.1, 1.1. So we got local extremum, but it's not what we wanted to obtain. So we got local extrema. I will show you in what sense. Now I will draw this surface again. So you see, this is g of A. This is G. So we have A and B are in the XY axis, and then we have values of GAB. And you see, for A and B, which are near 1.1, the local extremum is somewhere here. So when we choose our initial approximate 1.1, 1.1, we're in fact calculating local extremum of this function. This is the surface of this function. We are searching for the local extremum, which is in the neighborhood of our initial approximate 1.1, 1.1. So we will converge to the nearest local extremum to this 1.1, 1.1. And it turns out that it doesn't solve our initial problem, which we wanted. So to get the best fit for our 4 data points. So the initial approximate was bad in this case. Let's try with another. Let's say -1, -1. Now we know from the graph. Okay. Okay, we can look in the whiteboard. So from the graph, we know that A must be negative. So our function A times e to the power of bx, A must be negative since it must go, I mean, B must be negative. So e to the power of x is like that. And then e to the power of minus x is like that. So we know that this is for b bigger than 0, and this is for b smaller than 0. So we know that b must be smaller than 0. So our initial approximate was bad when we took b equals to 1.1. We should take something where b is smaller than 0. And let's try with b is equal to minus 1.1, and then also a is equal to minus 1.1. And run this. And okay. Okay, what we got. Okay, even if we took negative b, the method converged to positive b. So the method really converged. 0.18 was A, and then 0.43 was B, and we really achieved convergence because this difference is relatively small, 10 to the power of minus 18. But since B is bigger than 0, we know that this is again not a good local extremum for our problem. Again, this exponential function was positive. In this exponential function, B was positive. So even if we took, for the initial approximate, we took B which was negative, still the method converged to some solution with B bigger than 0. So the convergence is not, the solution is not good. The local extremum is not good for our situation. So let's try another approximate. And now what we do now, let's take still B negative, but let's take positive A. We can't know if the local extremum will be the one which we need, but we can try. Okay. And in this case, we got a good fit. From bare eyes, we can see that the fit is good. So it is exponential function, exponential model with negative b, and also it looks that it fits our data quite good. However, we see that in this case, the method needed 50 steps. So we reached the maximum number of steps in the final iterate, and the convergence was not, the convergence is not really good because the relative error is still 10 to the power of minus 3. So now at least we know that the actual solution is somewhere near 2 and minus 3, and we can try to improve this solution. Maybe we can try to run it with this as an initial approximate. So let's say that we'll run this with the initial approximate 2 minus 3. Let's see. Okay, still the approximate looks good. How about the convergence? Yeah, now the convergence is already better. After 50 steps, the relative difference is 10 to the power of minus 4. So improving this further, we could start another Gauss-Newton method with this as an initial approximate. Okay, so what I wanted to tell you with this example is that you have to check the solution at the end. So even if the method converges, so we saw that in the first two approximates, the method really quickly converged, but the local minimum was not the right one. So the method converges pretty quickly. But the local extremum of G is not the one we would like to find. And similar situation was observed for A naught B naught is equal to 1 minus 1.1 minus 1.1. However, for A naught B naught is equal to 1.1 and minus 1.1, the convergence is much slower, but the local minimum, local extremum is the one which we are searching for. So conclusion, the solution of Gauss-Newton method has to be analyzed at the end. So we have to answer on the question, is the local extremum the proper one? Okay, to finish this chapter with nonlinear models, let me only mention that this same problem could be solved using not Gauss-Newton method, but Newton's method. However, using Newton's method, there would be much more computations which would have to be done. And let's try to figure out how we would transform this problem into Newton's optimization, with which we started the second hour. So we have here our G, and so we have our G. So we have these points, we have this fitting function. We would like to solve this system. We put everything on one side, and then we are searching for the solution of the system with component functions G1. And since the system is not exactly solvable, we're searching for the solution by the least squares method, which means that we are minimizing the norm of the vector G1a, G2a up to Gma. So Gab is equal to 0. This is our system. So in the problem, we are minimizing the norm of Gab, which means, so norm, what is norm? Norm is a usual function. It's a function from R squared into R. So it's usual function. Because norm, this is some real number, some positive real number. And we started this hour with Newton's optimization. So we said that in Newton's optimization, we are searching for the local minima of a usual function, of a usual multivariate function, and you see this norm of G is just a special case of this. which means that we could use Newton optimization methods to find local extrema of this norm of G. So what we do is then, so we take F to be equal to norm of G. This is just square root, and we can square everything so that we get rid of square roots. So this is just G1 AB squared plus G2 AB squared and so on, plus GM AB squared. And then what we do is to do and then use Newton's method. As at the beginning of the second hour. So this means that what we do, so A naught, B naught is initial approximate. And then we improve it. So next approximate is then the previous one minus, and then we have Hessian. We said Hessian of F in the point AK, BK. So Hessian of F, and Hessian of F, what is this? This is, we have A and B. So it's F with respect to AA, then F with respect to AB, and then F with respect to BA, which is the same as AB, and then F with respect to BB. Calculated in the point AK, BK. I will write this evaluation here, and inverse of this times G, which is now gradient. So times gradient of F in the point AK, BK, and this gradient is, so it has two partial derivatives. So the derivative with respect to A, and then the derivative with respect to B. So you see, this is another way of trying to minimize G, norm of G. So minimizing norm of G then transforms the problem into Newton's optimization problem. And then we don't need Gauss-Newton method, but a usual Newton method. However, as you see, even in our example with 4 points, this would require a lot of computations, because we would have here sum of squares of those G1, G2, Gm. Then we would have to take derivative with respect to A and derivative with respect to B, collect it in this vector gradient of F. This would be long expressions, and then take also calculate all the second derivatives, derivative with respect to twice with respect to A, and then mixed derivative with respect to A and B, and then twice with respect to B. So using this Newton optimization method would require a long expression, a lot of computations already on the symbolic level, and then using MATLAB from that point on. Okay, this is everything for nonlinear models, and then next hour we start with curves. Is there maybe some question?
Yes, I have one question back for the example. How did we We multiplied the whole equation by -1. Where do we get that from? Like the equation was
you mean
of
here?
the form.
You mean
Yes,
here?
it was. Yes.
So since we are minimizing the norm, it doesn't matter if we multiply everything by minus.
Okay.
I wasn't careful. I wasn't consistent with what I wrote about, but it doesn't. It's not important. We could either put f from here on the right-hand side, and then our function will be y minus f, or we could put y on the left-hand side, and our function is then f minus y. Since we are minimizing the norm, it doesn't change a and b in the solution.
Okay, thank you.
Thank you for the question.
I've got one question also. So in this example, when the solution wasn't the one we were looking for, so the method still converges. But in this case, so where there are more constraints than variables, is it how many times does this method so that doesn't converges?
Oh, it's a very difficult question. It depends on the function, and there is no theory which would tell us which initial approximate to take so that we will know that the method will converge. It really depends on the function, and it's a hard question how to choose initial approximate so that the method will converge, and if it will converge, to which local extremum it will converge. So it's not possible to, so there are some theorems, but they are very messy, so they are not used in practice. There is one theorem which is called Cantorous Theorem, which ensures us which initial approximate we should take so that we will converge to our solution. But still, we need some knowledge about the solution, and then we have to do quite a lot of computations to determine where to choose for the initial approximate. So we cannot know in advance. Those iterative methods work in this way that we try different initial approximates. Of course, we try to choose initial approximate which makes sense. In this concrete example we did, the initial approximate which makes sense is the one where b is smaller than 0. So trying with b is bigger than 0 doesn't make sense. So meaningful b's are those which are smaller than 0. But then we don't know how to choose a. So we try different a's and different b's and look at the solutions if they solve our problem. Otherwise, we try with another initial approximate.
Okay, thank you.
Okay, if there are no other questions, then we proceed in 15 minutes, so 11:20. So in the last hour of today's lecture, we start with a new chapter which is called Parametric Curves and Surfaces. So curves and surfaces. So in the next 2 or 3 weeks, we'll study how to parameterize curves, how to analyze curves, and then we will generalize also to surfaces. And why we'll be doing this? Because in the dynamical models, so far we've studied linear models and now nonlinear models, and the third type of models will be dynamical models. So the dynamical models usually stem out of some dynamical processes which describe some motion, acceleration, and so on. And when we would like to describe some motion and calculate the velocity vectors and so on, it's natural to work with curves. That's why we have to understand a little bit about curves, how to parameterize them, how to analyze them, how to calculate the velocity vectors, some curvature, so how curved the curve is at some point. Then we will also see which points are singular, so the ones where we cannot calculate the tangent to the curve, or we will differ between points where we cannot calculate the tangent with the points where the velocity is 0. So these will be two different types of points. That's why we will work with parametric curves and surfaces for the next 2 or 3 weeks. But curve, this is nothing else than a one-dimensional object. So a curve is a vector function is one-dimensional object. So this is informally and formally now that we know a notion of a vector function, a curve is just some vector function, a parametric curve. Is a vector function f which maps from some interval into m tuples, and this interval lives in real numbers, is bounded, sorry, is a bounded or unbounded interval. So unbounded means that I could be, for example, real numbers, or it could be half line of this form. And bounded interval means that it's just an interval from A to B. Now, if we take m is equal to 2, we get just some curve of this form. So we have, let's say that this is our interval. And f is some path above this interval. So it is something like that. Okay. In fact, I wrote a picture. This was not a picture for m is equal to 2. This was a picture for m is equal to 1. Because for every t, why is this picture for m is equal to 1? Because here I wrote for every t, I prescribe the value of f of t. So this is t, and I have f of t is some value. And then for another t, let's say t1, this is some value, f of t1. So in fact, this green curve is just, this was just a vector function from r to the power of r. So m is equal to 2. For m is equal to 2, the picture would be still two-dimensional. However, our curve would be something like that. For example, like it could be like that. And here I have x and y, but this point, this is x, y at some t. So this is xy at some t. So x of t and y of t for some t. And I didn't write, I cannot write at which t. I could just here write, for example, t is equal to 1. For example, if at time 1, I would be in the point xy. So this would be a function f from r to the power of r squared. And f of t is then xt yt. This t is called a parameter. And why do we write it with t? Because it usually describes time. But it could be also other parameter, any other parameter. We will see different parameterizations of the same curve, but usually it's meaningful that t represents time. And for example, for m is equal to 3, then I have I have three-dimensional, I have a space and then one-dimensional object in the space, for example, some curve within the space. So this is a point x, y, z at some point t. Value of parameter t. For example, in Octave or in MATLAB, a few examples. Let's say that my t runs from the interval minus 3p over 4 to the interval to the 3p over 4. And then x of t is equal to t times cosine of t, and y is equal to t sine of t, yes. And I get some curve. If I plot this curve densely enough, then I will see the picture of this curve. And let's see what we get in this case. So you see, we get this curve. So we start here at t is minus 3p over 4. Then we increase t, and we are then tracing this path. For example, another picture. T goes from 0 to 4 pi. X is equal to cosine of t. Y is equal to sine of t. And let's say that there is no z. So we have x and y, which are cosine t, sine t. Then you remember probably from analysis that cosine squared plus sine squared is equal to 1, which means that x and y lie on the, for every t, x, y lie on the unit circle. And so as t runs over our interval, this xy, the point xy, runs over the circle. So let's say that I comment out this z, and then plot only xy. What I get is a circle. And even if I change this parameterization and say 2 times t, and here 2 times t, it will still be cosine squared 2t plus sine squared 2t. So the image won't change. See, the image didn't change. And even if I put here some let's say sine of t, cosine of sine of t, and then sine of t, as long as this argument is the same for both cosine and sine, we are tracing the same picture, so the same curve. Only that, yeah. So why did we got only this part? Because sine of t, when sine of t, why did we got only this part? Does anybody can anybody figure out why did we get only this part of the curve? So this is in fact still half of the circle, but it's not in the proper ratio. So here we have only x runs from 0.5 to 1 and y from -1 to 1. That's why it doesn't look to be half of the circle, but in the appropriate ratio, it would be half of the circle. But does anybody notice why we got only half of the circle? So if we look here, t is on the interval between 0 and 4 pi. Okay, sinus maps this interval from 0 to 4 pi into the interval -1, 1. So in fact, x, y then only go through the part of the circle where the argument is between -1 and 1. So I will write this here. Cosine of sine t, and then this is x of t, and then yt is sine of sine t. So this is xt yt. This is the set of the points when t runs over all possible real numbers. When t runs over real numbers, this runs over cosine of u, and then sine of u, where u is between -1 and 1. U is between -1 and 1. This is because sine t is between -1 and 1. So image of sinus is between -1 and 1. And we get only some part of the curve. So this is some subset of the unit circle. This is exactly that one. Okay, but if I choose here instead of sine t, if I choose something which is surjective, let's say t to the power of 3, and here also t to the power of 3. Notice that I have to, if I put t to the power of 3, then I will probably get error when I will try to run this. Yes, you see, I got error. Here, the error says that the one argument must be a square matrix and the other must be a scalar. Use power. So instead of just this hat, I need to use point hat. And this point dot hat tells me that I will plug vectors for the parameters. So here my t is some vector of values from 0.4 to 0, from 0 to 4 pi with 100 columns. But here, if I don't put t dot, then MATLAB takes this t as a scalar. So I can only plug in scalar for t. But if I want to evaluate this function on the whole vector, so on every component of the vector, I must tell MATLAB that I will be working with vectors. So I put here dots whenever I put, I would like to work with vectors, I put dots to the right-hand side of the variable. Now it should work. Yeah, so now it worked. Okay. Let's try again. Okay, this doesn't make sense. Let's try with T again. Yeah, so this is this is a sphere. I put now here 3 times T, 3 times T. It's still the same sphere, but it's at a different time. So point, if I use here, so x of t is cosine t and yt is sine t. So xt, yt this is a sphere, xy such that x squared plus y squared is equal to 1. And if I take, instead of xt is cosine t, if I take xt is cosine 2t and yt is sine of 2t, then I get the same curve, xt, yt is still a sphere, I mean a circle. But the difference is that at the different times I will be at the same point. So let's say that this is x1, y1, and then x2, y2. Here x1, y1, and x2, y2. So x1 t, y1 t is equal to x2, let's say s, and y2 s. If and only if, for example, one of the solutions will be s is t half. So this means that I trace the same curve only at different times. So if I this could tell me that I trace the curve with different velocity, but I will trace the same curve. Okay, let's look at this three-dimensional example I wanted to show you. So we have cosine t, sine t, and then z is, and then I have also the third argument, which is t over 5. If I project this on xy plane, I will still get a circle, but z will change, the third component will change with time. So it will be just if I drag circle in the third dimension, so we get a spiral. We'll see that we get a spiral. See, if I project this, I get only circles, but z grows, so get a spiral. For example, another curve. Another curve would be this one. So I have 2 times cosine and 2 times sine. And yeah, I can expect to get a circle of radius 2. So yeah, I get a circle of radius 2. So in what follows, we will try to figure out how to plot. So when we get, for example, the equation of some curve, how to plot it without MATLAB. So how to plot approximate picture of the curve and how to analyze behavior of the curve in different points. So how quickly we trace the curve. So what's the velocity of our tracing the curve, and where does this vector representing velocity points, in which direction does this vector points, and what can we say from the parameterization of the curve about the curve. So here we all knew that it goes for the circle, and we also saw that this circle can have many parameterizations, but for any curve, for a general curve, we won't be able to immediately see what's the actual curve, but we will study what can we infer from the specific parameterization. So in some parameterization, we will get that the velocity is 0. So x0, xt, and yt will be 0 at some point. And we will try to figure out, does this mean that the tangent to this curve doesn't exist, or is only the parameters of our parameterization such that the velocity is 0 in this point? So we'll study what can we say from the parameterization about the actual curve. Okay, let's try to figure out one example, so-called cycloid. So the question is, what path does the valve on your bicycle wheel trace as you bike along a straight road with constant speed? So what path does the valve on your bicycle wheel trace as you bike along a straight road? And let's say it's constant speed. Okay, so we have our, let's say we will need coordinate system. So let me draw coordinate system. This is y, this is x. So we start cycling. We have our bicycle, so bike, our wheel. And let's say that the valve is here at the beginning. And then we move along the x-axis with constant speed. Let's say that the speed is v0. So this center of the wheel moves with speed v0 in the direction of x-axis. And this valve, so it's, for example, here and here and then here. So we would like to describe the path of this valve. So it will turn out that something like that. And so on. So this is the path of the valve. Then next time we will also be able to integrate the length of the path. So we will have a parametric curve, and we would like to calculate the distance between, so the distance traveled when we moved from one point of the curve to the other. And so we will see how to calculate this path. But in this example, let's figure out what's the parametric equation of this green curve I've just drawn. So let's say that this is our center. So center C, center C has position xt, and y is constant. So it's always the position of the second coordinate is constantly the same. And let's say it's we can connect it with the radius of this wheel. So it's exactly r. So this is r for every t. This x of t is, we say that this bicycle travels with horizontal speed v naught, so it's v naught times t. And okay, we have our wheel, we have our valve. Let's say that we would like to describe the position of the valve. We have this valve V. What's the position of this valve at when C is at position xt r? Let's introduce this angle phi. So valve is at position. So position of valve is, so we have to subtract from xt. We have to subtract this part. So this part. And what is this part? How is this part connected with phi? In this case, it's so phi minus in this picture, when phi is bigger than 90 degrees, it's times cosine. So xt minus a times cosine of phi minus p over 2. And what's the y value of our valve? It's, we have to add to r, we have to add this part, and this is sinus a times sinus, so r times sinus of phi minus p over 2. So it's r plus a times sinus, r plus, not a, but r plus r times sinus of phi minus p over 2. Okay, but
real quick, what exactly is this a with the cosinus?
This a is r. Yeah, thank you. It's r. This is the this is this part. This is just the radius of the wheel. So this is r times cosine phi minus 50 degrees. So this is this red part. So the position of the valve is the position of the center, which is x of t. And then we have to subtract this x. And the second component is the position of the center, which is r. And then we have to add this part, which is r times sine of phi minus p over 2. And now, so this is x of t is v naught times t. We can connect this with the angle, in fact. So v naught. What is v naught? V naught, this is 2 pi over t, where t is, capital T is time for one rotation of the wheel. So when the wheel rotates once, it traces the 2 pi times a, in fact, yeah. 2 pi times a, since this is just the circumference of the wheel, circumference of the circle. So it traces the path 2 pi times r, not a. I have in my notes, I have a, that's why I'm confusing a with r. So 2 pi times r over capital T, which is the time for one rotation. So this is the speed, the horizontal speed of our circle, of our bicycle. Okay, so x of t is then 2πr over capital T times time. Okay, and I can write this as 2 pi t over capital T times r. Okay, and what is this 2 pi t over capital T? So the angle, this angle phi, let's look what is this phi. This phi is just 2 pi times t over capital T. So this is just our phi. So xt is then phi times r. So we plug this into our equation, and what we get is phi, so the position of the valve, x valve, y valve is phi times r minus r times, and then cosine of phi minus p over 2 is just sinus of phi, and then the second component is r, and then sinus of phi minus p over 2 is minus cosine of phi, so it's minus r times cosine of phi. So yeah, and this is, and then here phi goes from 0 to infinity. So this is our cycloid. Of course, in this picture, phi looks like it is between 0 and 2 phi, but we counted. So 3 pi means that the wheel already did one rotation, and then it's on the half of the second rotation. That's why this phi, in fact, goes from 0 to infinity. But when we calculate the position, of course, we calculate with respect to modulus 2 pi. So if we had 3 pi, then it's the same as phi. And this x of t is just phi, is phi times the radius of the wheel. Okay, let's try to plot this in MATLAB. Okay. So we have phi will be t. This is line space, let's say, from 0 to 10. And then x is our radius of the wheel, which let's say that it's 1. So we get a times phi, so t minus a times sinus phi. And then we have y, which is 1 minus, because a is the radius is 1, so 1 minus 1 times cosine. Okay, let's plot. Okay. Yeah, you see, we get the cycloid. Yeah, so this is the bed of the valve. So you see, it looks like it's not smooth. This is because line space, so it looks like it's not smooth. This was also the problem before when we were drawing the circle. So the problem is that this line space, since I didn't give the third parameter, which means how many divisions should MATLAB do. It did 100 divisions. So if you don't give MATLAB the third parameter, then it takes to be 100 in this line space command. And that's why the intervals are 0.4 of length 0.4. And it's not very dense. That's why it looks like the picture is that the curve is not smooth. This was the problem with circles before. So to improve this problem, we can put here 100, 1000, and draw the picture again. And now it looks much better, much more smooth. Yeah, we can return to the problem above when we have these circles. So line space between 0 and 4 pi, let's say that we have here 100, 1000. Okay, here we take t to the power of 3, or let's start with 3 times t. Let's see that if this will be a nice picture. So I have to comment out this. Yeah, so now it looks nice. Before it looked like it's not smooth. And let's try with t to the power of 3. Yeah, now the problem is, do you notice what's the problem? Why does MATLAB draw those lines? So in fact, we should get only the circle, but we get a bunch of lines within the circle. Do you know what's the problem? So the problem is that MATLAB, so when we do this parameterization, x of t is cosine of t to the power of 3, and then y of t is sine of 2 to the power of 3. And so our t is Lie space of 0 to 4 pi, let's say 1000 points. And so t's are then first point is 0, 0, then it's 0 something, so t1, so the second point, sorry, it's t is 0, then 4 pi over 1000, and then 4 pi over 1000 times 2, and then 4 pi over 1000 times 3, and so on. And then MATLAB calculates corresponding points, so x naught, y naught, xt, yt, you get 0, 0, and then we get cosine of 4 pi 3 over 1000, and then sine of 4 pi over 1000 to the power of 3, and so on. So the next point, cosine of 4 pi. Let me just finish this, and then we end. Sinus 4 pi over 1000 times 2 to the power of 3. And so on. So it calculates those points, and then it connects those points. And then you have another point, and it connects those 2 points. And since t to the power of 3 is high, those points are like that. So we start in, so the first point is not 0, 0, but it's 1, 0. We start in this point, and then the next point jumps here, and then the next point jumps here, and the next point jumps here, and so on. So in fact, what MATLAB does is this. So the problem is not that we really get this curve, but the problem is that our Lie space was not enough densely. We didn't have enough points in the Lie space command. So if we had enough points, then it would travel densely around this curve. Maybe we can put here 10,000 points. Yeah, in this point, now we don't have this problem of jumping from one side to the another again, but still it's not dense enough so that we won't have this jumping up and down, up and down. We can try with 1,000,000 points. Yeah, with 1,000,000 points, we really get the circle. So theoretically, we should get the circle, and yeah, the problem that we didn't get a circle at the beginning was that we had not enough points. Okay, this is all for today. Are there maybe some questions? Sorry for taking you 5 minutes. We will stop 10 minutes earlier next time.
I would just like to check for the homework You said last week we could expect this week, but I can't find it on the Moodle, so I'm just checking.
You will get it.
Okay, no problem.
Will be probably during weekend.
Okay, thank you.